Okay guys, so today we're going to be taking our set notes and all the information and things we learned about sets, and we're going to apply it to something called a union, and then we're going to apply it to something called an intersection. So we still got to be pretty proficient with sets. So we'll start off here with an example where we've got marbles being pulled out of a bag. So marbles labeled 1 through 7 are in a bag. S is defined as the set of all outcomes when one marble is pulled from the bag. All right, so S is just everything that could happen. So let's start by just defining S. S is going to be all my numbers 1 through 7. All right, so there's my set S. Then it says, let A be the event of pulling an even number and B be the event of pulling a prime number. So what are my even numbers here between 1 and 7? Well, that's just going to be 2, 4, and 6. So subset A contains only these three numbers, and B contains all my prime numbers. So my prime numbers, remember 1 is not prime, but 2 is, 3 is, 5 is prime, and 7 is prime. So B has 4 numbers in its set. So what we have here is we have a set, and then we have 2 subsets of that set. All right, so what we're going to do is we're going to construct a Venn diagram to represent the set S. So a Venn diagram to represent everything that's going on in here. So a Venn diagram is just 2 circles. They're not going to be perfect. And I'm going to box in these circles because set S might contain some things that are not in this Venn diagram, right? I've got A and I've got B, but there might be some elements of S that are in neither, and so we've got to have a place to put those. So in this Venn diagram, I've got to figure out what goes where. Well, it looks like in A, I have 2, 4, and 6, and in B, I have 2, 3, 5, and 7. Well, one thing to note is that 2 is in both of those. So I've got to make sure that I put my 2 here, and then I'll put my 4 and my 6, and I'll put my 3, 5, and 7, and now I've got to check, are there any elements of S that have been left out completely? Yes, the 1. So the 1 has to go outside, all right? So that's just a Venn diagram that represents everything that's going on in S. So this is where we get into some new stuff, new vocabulary here. This says to calculate the probability of A union B. So we've got to define a union here. So what a union is, unions are just the probability of A happening or B happening. All right, so what I'm saying here with this, the probability of A union B, is I'm saying what is the probability that we pick a number that is either even or is a prime number. That's what this means. So how can we calculate that? Well, let's go back to our regular formula, right? If I want to find the probability of something, even if it's something like this, I know that I need to find the number of elements that are in this set and divide it by the total number of elements in the original set, right? So how many elements are in this union? How many things here are in either A or B? I think the easiest thing here is just to go element by element and count them. Is 1 an element of A or B? No, it's not, so 1 is out. 2 is an element of A or B. Even though it's in both, it's still in one or the other, so it counts. 3, 4, 5, 6, and 7 are also in either A or B. So it looks to me like I have 6 elements that are in either A or B out of the 7 total elements. So the probability of this union of 2 events is 6/7. So that's what a union means. A union basically is saying, and maybe we can just use blue here. A union is saying, I want everything that's inside this Venn diagram. Anything in the middle, anything in either side. It all counts. All that stuff is in my union. All right, now this is different over here. This is saying calculate the probability of A intersection B. So let's define an intersection. As I'm sure you can imagine, an intersection, instead of using or, we're going to use and. So what we're asking for here is we're saying what is the probability that we pick something from this set S that is in A and is in B. So in this case, it's a little different. We're looking for now something that's in both. It's got to be in A and it's got to be in B. So it's only going to be the things that are in that overlapping space. All right? So if I'm going to calculate the probability of something being in A and in B, their intersection, I need the number of elements that are in A and B divided by the number of elements that are in set S. Well, again, we have 7 elements in set S, so we've just got to look how many elements are in the overlap, meaning they're in both, and that's just 1 element, so 1/7. Okay. The last question here is just one to get us thinking a little bit. It says, why isn't the probability of A union B, or the probability that I'll choose something that's in A or B, equal to the probability of A plus the probability of B? So let's just think about that for a second. If I have the probability of A union B, what we're saying here is that this will not equal the probability of A plus the probability of B. Or to put this into just words, it's saying, why isn't choosing something that's in one or the other the same as taking all the things in one and adding it to all the things in the other? Why doesn't that equal out? Because it seems like it should, right? If I want to know how many people are either red-haired or own dogs, why can't I just take all the people who have red hair, add them up, and then add up all the people who have dogs? It just doesn't work that way, and you're going to see that in a second. Because if I take the probability of A union B, which we just found out is 6/7, and set it equal to what we have over here, well, we've got to find out the probability of A. So what would this be? The probability of choosing an element in set A. Well, let's go back up here. I see 1, 2, 3 elements that are in set A out of 7. So the probability of me choosing something in set A would be 3/7. And the probability of me choosing something in set B would be 1, 2, 3, 4/7. Well, 3/7 plus 4/7 is 7/7, or 1. And clearly 6/7 is not 1. So why is that? I'm sure many of you guys have already figured it out. This doesn't make sense. You can't just add up all the A's and all the B's, because then you will have double counted this too. You'll have already counted this, right? When we counted up all the A's, we counted up 2, 6, and 4. And then we counted up all the B's, and we counted 2, 3, 5, 7, and we double counted the 2, so that's why we have too much stuff over here. So this leads us into a really important formula, because we're going to end up using this logic to calculate unions when we don't have all the information sitting in a Venn diagram for us, because it's not always going to be that easy. So here's our union formula. If I want to calculate the probability of A or B happening, then what I'll do is I will add the probability of A plus the probability of B, but that means that I've double counted their intersection, right? If I add A and B, I've double counted this. So all I'm going to do is subtract one of these to eliminate the fact that I've double counted it. So I'll just subtract their intersection, right? So I'll just take all of my even numbers plus all of my prime numbers. But when I do that, I double counted 2. So if I subtract 1, 2, then I'm fine. So I'll just add all of the elements of set A to all the elements of set B and subtract their intersection. This is a formula that's going to start to come up pretty often when we're calculating unions. So we'll want to keep that in mind. All right? I'll see you guys tomorrow.